about dot products and vector projections. Vector projections is actually what we're going to use when we get to the work piece. Vector projections is where you get your work formula from that you learn in like a physics class. So it says, using the definition of magnitude of a vector, we can find it's squared. And so we are going to take just the distance formula. That's what we're going to use here. We're going to say, from what we know of distance formula, we will take our A1, that's our ending, right? Our A1 minus our B1, that's just our x's, right? Think of it as x's. So we'll say A1 minus B1 squared, that's my x1 minus x2 squared, right? And then my A2 minus B2 squared. You could do x's and y's here if you wanted to. So if you wanted to, you could say, well, x1 minus x2, right? And square it. And then y1 minus y2 and square, right? That's the same thing. We're just using it with the a's and b's because that's what they gave us, all right? And so when I do this formula out, it said that that is really the formula for the actual vector length. That's what we've done. But they want it squared. So if I square both sides here, what happens?
Goes away.
Yeah, my root goes away. So I'm left with just A1 minus B1 squared plus A2 minus B2 squared. So far, so good? And then I'm just going to FOIL it. So foiling we're familiar with. So when I FOIL, I end up with this first one squared minus 2 times the ones added together plus the last one squared. And that's what happens on both of these. So I end up with A2 squared minus 2 A2 B2 plus B2 squared. All right? And if we were to simplify this part of it, so if we were to group the A's, so we'll group the A's, which is what they do here. A1 squared plus A2 squared. We have that. That's just how we would represent this. Remember when we have it in composite form, it's just the two of them squared, right? And then we have B1 squared plus B2 squared. That's just represented by this, right? And then we have these groups. So we have minus 2, and I'm going to factor that out. And I have A1, B1, right? Plus A2, B2. Okay. Because I pulled out a negative 2 out of both of those. All right. And so what happens here is we have this little guy right here, this piece of it. This is where we get what's called the dot product, all right? This piece of the puzzle here, if I were to take my, and I'm going to replace it with x's so that you can see it. So x1 times x2 plus y1 times y2, that little piece of it. And they use it, the formula has a's and b's, but I want you to remember what it represents. It just represents your x's and y's. But the formula shows us it as a's and b's. So when we get to the formula, I want you to know that's all they're talking about. This piece of it is called the dot product. The dot product. All right? It is notated with a little dot in between it. It almost looks like multiplication, but they're talking about vectors here. So they will be bold letters with a dot in between it, which means they're talking about vectors, and they want you to use the component form of those vectors. All right? And so that is called the dot product. That little chunk of what we just did is called the dot product. And that's where they get it from. They get it from the magnitude formula squared. All right. You don't have to remember the proof of it, but I wanted you to see where it came from. All right. And so here's the form. The dot product of A, this is a vector in component form, and B in component form is represented like this. This is how you'll see it notated. A dot B, the bold lets you know they're talking about vectors. And you're just taking the two x values from the A and the B, multiplying those, and adding the product of the two y values. Those a1, b1 represents the x's, and the a2, b2 represents your y's. All right? It yields a scalar. So the dot product yields a scalar. It does not give you direction when you do a dot product. All right? We are going to use dot product in other formulas. Okay? So you are learning this formula because we're about to use it in other things. We're going to use it to find angles, and we're going to use it to find work. All right? If those two vectors, so if the dot product ends up being 0, it happens sometimes, and we're going to give examples of that. If the dot product is 0, then they are said to be orthogonal. Orthogonal. And so you may have seen that word possibly in physics, orthogonal. But if that's 0, they're called orthogonal. It's a special type, all right? So we're going to do an example, finding the dot product and then telling us if it's orthogonal or not. All right, find the dot product, determine if it is orthogonal. So the first one, they want the dot product. Well, the dot product is going to be my 3 times my negative 4 plus my 6 times my 2. What is 3 times negative 4? Negative 12. 6 times 2, 12. My dot product is going to be 0. And yes, they are orthogonal. They're orthogonal. All right. Easy. Let's look at the next one. My dot product is going to be 2 times 8 plus 5 times 4. All right. 2 times 8 is 16 plus 20. My dot product is 36, so that is my dot product. But no, these are not orthogonal. All right, check your work for the first one. Negative 17 was your dot product, and no, this is not orthogonal. And then for the second one, yes, your dot product was 0. So in the middle of this page, the properties of dot product. Commutative property, order does not matter when you find dot product. It does not matter which one's first and second because you're multiplying and adding, right? So both of those properties are commutative, so the overall property is. Distributive property, you can do a dot product to a sum. Scalar, you can multiply a dot product. 0 vector, if you multiply a dot product by 0, it will be 0. And then if you have 2 dot products, it will be squared, like it's the same concept. They do talk below about using dot product to find magnitude. I think using dot product to find magnitude ends up being confusing because you end up doing the dot product of the 2, and then you take the square root, and it ends up being just the formula you already know, which is the x squared plus the y squared with the square root. So I feel like it's easier just to go back to when you need to find magnitude. Make sure that you know that little absolute value looking sign means to find your magnitude, right? But other than that, I wouldn't use dot product to find it. I would just use my x squared plus my y squared and take the square root, just because it's simpler than trying to plug it in with dot product. All right, so let's look at angle between two vectors. Turn to page 502. If theta is the angle between two non-zero vectors A and B, then the cosine of theta is going to equal the dot product of A and B over the magnitudes of A and B, okay? So this is a formula you will want to memorize here. This is a way that you can find the cosine or find the angle, all right? So if you have the vectors, then you can find the angle that made those two vectors together. So they give the proof. The proof is based on the law of cosines. That's where the proof comes from. And they do the proof out. They started with the law of cosines, a squared plus b squared minus 2ab cosine of theta. That is the law of cosines. And then they simplified it to what it equals on the right-hand side. And when you simplify it all out, you get the formula that I've told you to memorize. So unless you want to try this proof every time, you may want to memorize the formula. But the dot product of the vectors over the magnitude of the vectors is what we're doing here. All right, so let's look at example 3. Find the angle between vectors u and v. Angle between vectors u and v. Obviously, when they when you give something like this, they're actually not going to give you the angle. So you would have the vectors, maybe not on a graph, but you're welcome to draw them on a graph. In component form here, you know it's a positive 6, positive 2, so you know that vector is in the first quadrant. Negative 4, positive 3, that's second quadrant, all right? And they're facing opposite directions based on the fact that how this is drawn here and how they've given you the vectors. So we're going to do exactly what the formula called for. I put the formula back up here, right? This is the formula we're using up here. The dot product. So the first thing we're going to do is the numerator is going to be the 6 times negative 4 plus the 2 times 3. That's my numerator. The denominator is going to be my magnitude of the individual ones. So the magnitude of 6 squared plus 2 squared. And the magnitude is negative 4 squared plus 3 squared. All right. So simplifying this, we have negative 24 plus 6. So my numerator here is negative 18. All right. Over here, 36 and 4 gives me the square root of 40, right? And then 16 and 9 give me the square root of 25.
Are you multiplying them?
Yes, those are being multiplied. Now what I would do is I would simplify these first, okay? So I would take, like, this is going to simplify to 5, right? And this is going to simplify to 2 squared to 10, okay? And then I would multiply those. So my denominator is going to be 10 squared to 10, all right? This tells me the cosine. They want the angle. So if I have the cosine and I want the angle, what do I need to do? Right, so I need to say cosine negative 1, and you can put all of this right into your calculators. Divided by 10 squared to 10. You use your positive and negatives here because it does affect your cosine. We're not using reference angles. 125 degrees. So go ahead and try that. Make sure you put it in correctly. In your calculators, you want to do your cosine negative 1, 18 divided by 10 square root of 10, close, close. Look at the next one. We have 3, 1 and 3, negative 3. So we're going to do the dot product here. 3 times 3 plus 1 times negative 3. And then the denominator is going to be the square root of 3 squared plus 1 squared times 3 squared plus negative 3 squared. All right, in the numerator, we get 9 plus negative 3, right? So we get 6. In the denominator, this is going to be square root of 10, and this is going to be square root of 18. So we get, this doesn't simplify. This simplifies to 9 square root of 2. All right. But this, when we do this, it's going to be times the square root of 10. So we have 9 square root of 20. This will simplify more. The 4 can come out. So you end up with 18 square root of 5, right? Pay attention to your, how you reduce these. 18 square root of 5 here. Those will reduce as well. So just so you can see it over here on the side, if I have a side, if it'll let me move this out of the way maybe. All right. When you have square root of 10 and square root of 18, you can do all of your factor tree here. 2 times 9 and 3 times 3. And anything that pairs up, the 3's pair up, the 2's pair up. So that's how we get 6 square root of 5, just as a reminder when you're doing your factor tree there. All right, check your work for the first one. Should have gotten 156.8, or if you rounded to 157. Does anybody need to see this one?
Yes.
All right. So we'll do the dot product first. We have negative 5 times 4 plus negative 2 times 4. In the denominator, we have the square root of negative 5 squared plus negative 2 squared. That's my first one. I made that a little big. And then The second one is 4 squared plus 4 squared. So this is negative 20. This is negative 8. So my numerator is negative 28. In the denominator, we have 25 plus 4, which is 29. And 16 plus 16 is 32. So far, so good. We can simplify a little bit here. 29 we can't simplify, but 32 we can. 32 we can take a 4 out, right, and square root of 2. So we end up with negative 28 here. We end up with 4 square root of 58, which is kind of hideous. This reduces, right, the 4. So in your calculators, you do cosine negative 1 of negative 7 divided by the square root of 58, which should give you this number right here. When you do this, this is going to be the 32. 32 is going to be 2 and 16 and 4 and 4, right? So the 4 comes out, and then I'm left with just a 2, so I multiply the 2 and the 28. Those are both in the root. That's where I get the 58. I mean, the 2 and the 29 gives me 58.
Okay, got it.
So I'm going from the start of U to the end of U. What they're saying in all of this craziness here is this vector is made up of 2 movements, correct? In order to get from point A to point B, technically I had to go right and up, all right? And so if they are seeing the force or the work or whatever we're going to be using this with of U projected onto V, then what they do is they use the right movement that is parallel to V. You'll see that the right movement of U here is parallel to vector V, right? And so this formula helps you use these components to get your overall. U is made up of W1 plus W2, all right? And so we use this to find the projection of U onto V. And then we write, now that we know V, we write U as a sum of this one plus that one, all right? So the first thing we're going to do is find it. It says find the projection of U onto V. So we are going to do this little process here. U onto V. We are going to say the dot product between the two. So we're going to say 3 times 5 plus 2 times negative 5. That is going to be over my magnitude of V. V, all right? So my magnitude of V squared. So what happens if I do the magnitude of V squared? The square root cancels. So I don't even have to worry about this square root, right? I just have to do the first one squared plus the second one squared. But I want to show you why that happens because the formula has it squared. So I'm going to say 5 squared plus negative 5 squared. All right, and that is times my vector V, which is 5, negative 5. So I want to simplify this first before I do scalar multiplication here. 3 times 5 is 15. All right, so I have 15 plus negative 10, so my numerator is going to be 5. Here I have 25 plus 25, so my denominator is going to be 50. I can reduce that, right? So I have 1 over 10. And that's multiplied by 5, negative 5. So my projection is going to be 5/10 or 1/2. And negative 5/10, negative 1/2. That is my first. I have actually found by doing this, W1. That's what I found. So the projection of U onto V is W1. That's this guy right here, W1. All right. All right. We know that U equals W1 plus W2, right? That's the movements, W1 and W2. We established that already, okay? I know what U is, right? What is U? U is 3, 2, right? It is, so, but we're going to plug it in. U is 3, 2, right? If I already know what W1 is. If I'm trying to find W2, I'm going to subtract W1, right? Subtract. I found W1, 1/2, negative 1/2, right? And that will give me what the second movement was, W2. Okay? Make sense? So then I just subtract. I mean, that's just a matter of literally subtracting the numbers. 3 minus 1/2, well, that's 6 halves minus 1/2. That's 5 halves. And then 2 minus a negative 1/2, that's 2 1/2, right? That is also 5 halves. So that's W2. So if you wanted to write U as a sum of two of them, you would say U is going to be W1, that's this one, 1/2, negative 1/2, plus W2, 5 halves, 5 halves. That's what makes up those two forces there. All right, vector projection. So if a vector U represents force, then the projection of U onto V represents the effect of that force acting in the direction of V. For example, if you push a box uphill, this is right above it, in the direction of V with the force of U, the effectiveness of the force is a component push in the direction of V with projection of U onto V. They give us this picture. We have a 3,000-pound car sitting on a hill, inclined at 30 degrees as shown. Ignoring the force of friction, what force is required to keep the car from rolling down the hill? All right. One vector is given to us by the force of the car. The other one is given us by the angle of the slope. Okay. You're going to assume a unit vector here. By unit, I mean like think of unit circle. Okay. Think of unit circle. So the force of the car is pushing down, but not left or right, okay? The force of the car, the gravity of the car is pushing down. So how would I write a vector that's pushing down with 3,000 pounds? It would be negative. What would my x would be what though? My x would be 0 actually, and then it would be negative 3,000. That's the vector of the gravity of the car, all right? The second vector is going to be from this 30 degrees. The angle is trying to move it left and right, up and down. All right, the angle, all right? So for the angle, I am going to use sine and cosine. X is which one, sine or cosine? Cosine. Remember, your x is your cosine, yes. So the cosine of a 30-degree angle is square root of 3 over 2. The sine is my y, that's 1/2. These are my vectors, okay? My vector is the projection of the force onto this. So when I do this, it's going to be F and V. So this is going to be my V, right? This would be like the U in the other example. The other one would be like the U. The force would be like the U. Okay? So before we would say the projection of U onto V, right? And we did our formula. Now we're saying the force onto the incline, all right? And so we're going to do the same thing. We're going to do our dot product. Consider this to be like your U and that to be your V, all right? So the dot product is going to be 0 times anything, right? There we go. That's 0 times square root of 3. That's just going to, over 2, that's just going to be my 0. Plus my negative 3,000 times my 1/2, all right? Make sense? Over, my V is a unit vector. So the magnitude of my unit, if it's unit circle, what is the magnitude of my unit? On a unit circle, what's the length of any unit? What is your R on your unit circle? Your radius. It's called a unit circle for a reason. Oh, goodness. Yes, your unit is 1 because we use just our unit here, right? So we have over 1 times 1. That's my unit for both of those, okay? So we end up with just 0 plus, what's negative 3,000 times 1/2? Negative 1,500 times my V here. V. Because my magnitude is just a 1, we're going to use the 1 there. So negative 1,500 times your 1. That means it's 1,500 pounds of force in the direction. So direction of the hill is going to be sloping down. That's why it's a negative. You don't have to put force in terms of negative or positive. Usually just tell it. It's like in the direction of the hill. So it's 1,500 pounds of force, right, is what it's going to take against the incline of the hill. It's going to take 1,500 pounds of force to keep that car from going down the hill. This is what you're familiar with physics, all right? So another application of vector projection is the calculation of work done by force. Consider a constant force F acting on an object to move it from point A to point B as shown in the figure. If F is parallel to AB, then the work required is the magnitude of the force times the distance from A to B, or force times the magnitude of that vector. To calculate this, to calculate the force, we use projection. So the projection of the force onto the vector AB times AB, right? And then they show you this little proof over here to the right. So I'm going to walk through this with you. So we have the cosine, right, is the projection of AB over F, all right? Why is that? Well, we have this angle right here. Cosine is adjacent over hypotenuse, correct? The adjacent is the projection. The hypotenuse is the force itself, okay? So we know that the cosine is this. So we could write it this way. The projection is force times the cosine. Does everybody see that? All I did was multiply both sides by the F. The projection then is force times the cosine. So my work formula is the projection of this vector onto the AB, the projection of the force onto the AB times the magnitude of the vector. That's my formula here, right? If I replace that, the projection with what I just found out the projection to be, then you end up having the force times the cosine of theta times the magnitude. Magnitude is just distance, correct? So force times the cosine of the angle that you're applying the force times the distance of the vector. This is where your work formula comes from in physics. It is a vector-based formula, okay? So what are they saying? A person pushes a car with a constant force. They just gave me my F. Force of 120 newtons. At a constant angle. They just told me what to take the cosine of, 45 degrees as shown. Find the work done in joules moving the car 10 meters. They just gave me the magnitude of my vector, right? So we're going to take my force, 120, times the cosine of the angle that the force is being applied, times the distance of how far I am applying that force. And that is the work that's going to be done, 848 joules. Yes, 848.5 joules. All right. So you can use the dot product of those, which is what they show you. I feel like the dot product is more difficult. All right. The dot product works the same. The force is going to be 120 times your cosine, 120 times your sine, times your 10, 0, because you're moving it right. So if I did the force method, I would do the same thing basically, 120 times my cosine of negative 45, because that's the angle that I'm using from this direction. That's my A and B. Rather, it works out the same though, using those two formulas. So they just did a dot product between that and I'm moving it right and not up and down. So if you did the dot product of these two, you would get the same exact answer as using this formula. All right, it works out the same. So I find this formula easier than the dot product formula. All right, so try guided practice 7.
Wait, so
All right, so for this one, you should have done force 85. The angle at which you're applying the force was cosine of 60. And he pushes the vacuum 6 feet. Your final answer for this should have been 255 foot-pounds. Your units will be in whatever they gave it to you in. And this, the first example, they gave it to us in joules, and this one they gave it to us in foot-pounds.